Sorry. We're going to have to edit it. Sorry, I'm using Dustin's computer. Okay, next up, we have another talk that was rescheduled from the 2022 JMM special session on recent advances in packing. Our speaker is Alexander Barg, who is a professor at the University of Maryland, College Park. Professor Barg studies mathematical problems of information and coding theory, related problems in distance geometry and combinatorics, as well as random models of managing and processing information. Today, he will tell us about bounds for the sum of distances of spherical sets of small size. Please take it away, Sasha.
Thank you. Indeed, this is about bounds for the sum of distances, and this is a joint work with Peter Boyvalenkov and Maya Stoyanova, both from Sofia, Bulgaria, Peter from the Mathematical Institute, and Maya from the university. Sorry, give me a second. Yep. Yes. And as an abstract of the talk, what we do, we compute bounds on the sum of distances using linear programming, and we construct a few examples to see whether how far or close they are to the bounds. We do not reveal any new minimizers or maximizers for the sum of distances, but there are some examples that nevertheless seem to be good if one looks at the bounds, compares them to the bounds. Now, the sum of distances problem, of course, is a very classical one. We start with a spherical code, which is nothing but a set of endpoints on a unit sphere in the real space, and consider the sum of pairwise distances, Zi minus Zj, Euclidean distances, so the chords, and look at the largest possible sum over all codes, Zn of a fixed cardinality. And the problem was introduced by Laszlo Fejstóth, 1956, and there has been quite sizable literature on this question for the classic setting of the problem. Now, the classic setting assumes that the dimension is fixed and the cardinality goes to infinity. Introducing the average distance on the sphere to state the bounds, so the average distance is nothing but the average of pairwise distances over all the points on the sphere. This is an easily computable quantity, and this is the explicit expression. So then the difference between this scaled average distance and the sum of distances in any code of size n on the sphere is non-negative to begin with, and we shall remark later why. And then there are bounds from below and from above. So essentially the asymptotic order is known. And there are two constants that account for the lower and the upper bounds. The upper bound is due to Ralph Alexander, 1972, the lower bound to Joseph Beck. A refined asymptotic is the second term, or maybe even all the terms were computed by Brauhart, Hardin, and Saft, 2012. And there was an extension to Rees energies, so where we put a power S here by Arno Kaulars and Ed Saf, 1998. And as a parenthetical remark, so we look at the chordal distances, but a sum of geodesic distances. So the arcs has also been considered, also due to Fejstóth. And I will refer you to the paper by Dima Belik, Feng Dai, and Ryan Matsky in 2018, who discussed and advanced this problem for the geodesic case. Now, our setting is different from the classic one. In coding theory in general, information theory, and in some other applied areas, it is natural to do the following. Let the dimension grow and let the size grow in proportion to the dimension. So remember, it had been fixed, now little n is growing. Let us say that the size of the code is proportional to the dimension and to the power alpha, and small size for us means that alpha will be at most 2. There is an easy upper bound. I'll later explain how that is derived, why it is easy, which says that the sum of distances at most n square times √2. So how does this work? What is this about? In large dimensions, remember, n goes to infinity. If we want a large sum of distances in the code, what we do, we take a point and we try to place all the other points as far as possible. Well, not at the opposite of the sphere, but on the orthogonal hypersphere, because if we place them there, then they will manage to be far away from each other, while also being far from the point that we have fixed. And so the distance from the point to all the other points is more or less √2, the unit sphere. And there are n square pairs, and that is indeed a good intuition for this upper bound on the sphere. And at the same time, if we would like to derive some lower bound on the sum of distances, then of course we need to assume that the points are well separated. So there is some minimum separation between the code points, because otherwise we could place as many points as we wanted, and the distance would still be arbitrarily close to 0. So assuming minimum separation, we can also derive lower bounds on the sum of distances. As a remark, let us recall that the quantity called quadratic discrepancy of spherical codes, which is related to the sum of distances, as we shall see in a moment. What is quadratic discrepancy? Let us define a spherical cap. A spherical cap is a metric ball on the surface of the sphere. So it has center at x, and it is formed of all the points y, whose inner product with x is at least t. So the cosine is t of the angle. So a spherical cap of radius inverse cosine of t and center at x. Now, take a random point x on the sphere and look at the normalized number of the code points. The code is fixed in that cap. Subtract the average number of code points in the sphere, which is more or less proportional to the surface area of the cap. Let us take a square of that and integrate on all x, which, as I said, can be thought of as being random. And then this is nothing but the variance, or proportional to the variance, of the number of code points in the cap. Now, after that, we integrate over all the radii of the caps and call this quadratic discrepancy. This quantity is among classic quantities in distance geometry on the sphere. And a very well-known Stolarski's theorem is called the invariance principle, says that this discrepancy can be expressed as the difference between the average distance on the sphere and the average distance in the code, where the proportionality coefficient again is explicitly computable. Now, this is a variance, or maybe an integral of the sum of the variances. So that is why this is non-negative, and that is why this difference is non-negative. And that's how the bound that we discussed on the previous page indeed comes into existence once we import the known bounds on discrepancy. All right. Yes, and this is what this page is about. Discrepancy is non-negative, and so the sum of distances in any code is at most √2 n square. Here is the second term, and for the third term, we have something proportional to 1 over the square of the dimension. This non-negativity, in fact, is a manifestation of the Kabatansky-Levenstein so-called inequality about the mean, which says that for non-negative different functions, or rather the distance is a negative different function, so the average over the entire space is at least the average over the subset, or any subset. And this has been further discussed in the work by Peter Boyvalenkov, Peter Dragnev, Ron Hardin, Ed Seff, and Maya Stoyanova in 2019. They in fact have a whole series of papers on this subject. So that's an upper bound anyway. This series of works by Peter Boyvalenkov and his co-authors deals with linear programming bounds on any geospherical codes. Let Us consider a potential energy H, and then the potential energy of the code is the sum of all the possible, over all the possible pairs, H, X in a product with Y. And we can define the smallest possible energy and the largest possible, but now the largest possible requires minimum separation. And you may remember that I had this largest and smallest switched previously, but this is because the distance is negative definite, and here we want positive definite functions. So we change the sign, and the minimum and the maximum exchange their places. So in any event, this is the minimum energy, maximum energy of the code with respect to the potential H. Linear programming works well if the potentials are absolutely monotone. So the derivatives are all non-negative for all values of the argument from between -1 and 1. The LP bound was pioneered by Udin, 92, and of course the well-known paper by Henry Kohn and Abhinav Kumar, 2007, where they in particular proved that sharp configurations are minimizers of potential energies for all absolutely monotone potentials. Not extending this work, but working on the same problem, this group of 5 authors, Peter Boyvalenkov and his co-authors, published a series of papers from 2016 to 21, where they, in Kohn-Kumar, so the minimizers are sharp configurations. A sharp configuration is a spherical code which has few distances between its pairs of points and at the same time forms a spherical design. So such sharp configurations are indeed energy minimizers. In contrast, the universal lower and upper bounds by Boyvalenkov and his group depend only on the dimension and cardinality. And so that is why they are termed universal bounds. They don't know much about the code except for the dimension and cardinality. And those LP bounds are obtained by constructing a polynomial, a test function. That is, the important property is that it's below the potential for all values of the inner product that may be realized as distances in the code, or if we want to ignore the code, do the universal bounds, then for all t between -1 and 1. So this is the setting, and then universal lower and upper bounds on energies were derived in the cited papers in the following form. This form will not tell you much because it involves parameters from the Levenstein bounds, summarized in his work of 1992, for instance. But in any event, it is possible to write lower and upper LP bounds on energies. So that was the main accomplishment of the previous works on this problem for general potentials, not necessarily the sum of distances. And as we see, there is a pair of bounds, lower and upper, for every degree of the test function, starting with linear test functions, quadratic, cubic, and so on. And it looks good on the surface, but these bounds are difficult to compute. So this is still not the final word on this problem, but at least we have a general expressions that we can try to work with. So this is what we did. We took the potential to be the negative distance to make it positive definite, absolutely monotone. And again, we attempt to bound two quantities, largest possible sum of distances, smallest possible sum of distance, where for the smallest, we assume that some value of the minimum separation in the code. And the same approach works for potentials of this Rees form for half integer powers. Even though we ourselves did not work on this, on the general potentials. So there are some universal upper bounds from the linear polynomial, quadratic, cubic. Again, I will not say much about them because the formulas are difficult to grasp, to process. And there are some lower bounds, again, linear, quadratic, cubic. And the cubic is already too long to be stated here. In fact, it takes some work to compute it. even though the result again is not terribly intuitive. Well, the lower bound is intuitive in the sense that it is trivial, because as we said, S is the minimum separation. So root 2, 1 minus S is the minimum Euclidean distance. And the linear lower bound just says that the sum of distances is at least the minimum distance times the number of distinct pairs. So not a terribly clever bound, but the quadratic and cubic cases yield non-trivial results. Let us look at what we get in asymptotics. We obtain root 2n square main term will persist. And then for the linear upper bound, we have the second term n over 2, a somewhat better term for the quadratic bound. And yes, and even better term for the cubic bound in the range of its applicability. The cardinality of the code is for this cubic bound, third degree bound, delta times n square. N square is the dimension. Right. Well, there is a link to quadratic discrepancy of binary codes. In the interest of time, I will skip that because, again, in this work, this is more a remark than one of the main results. Let me just skip that. And perhaps the most interesting part of this story is examples that we constructed. So having these bounds, we said, what do spherical codes that we know or can think of, what do they give in comparison to the bounds? There are multiple sources of spherical codes, for instance, equiangular lines, tight frames, binary codes, of course, that can be turned into spherical codes very easily. We simply take a binary and place it on the sphere by changing a 0 to 1, 1 to -1, and normalize for the unit radius. That immediately gives us a spherical code. So let us look at what we are getting. Let us take, for instance, the Dominique Descant's family of equiangular lines. And simply, each line pierces the sphere at 2 points, take them and include them in our code and do that for every line. So that's a spherical code. The parameters are the dimension, the cardinality, the minimum separation for any integer r greater than 1. Famous family, the first example of a quadratic sized family of equiangular lines constructed from Quadratic sets of lines related to Quadratic codes and so forth. Computing the sum of distances, we obtain an asymptotic expression of this form. And conveniently, the dimension grows and the cardinality grows in proportion. So this is a good place to look for examples for our asymptotics. So this is what we get for that equiangular lines, and this is what the bounds give with that cardinality and that minimum separation. So this is the lower bound, this is the upper bound, and as we see, the order in the second term in the upper bound coincides with the actual value, except for the constant. So they follow the upper bound rather well, and we compute a few numerical examples. Of course, the dimension and the cardinality grow quickly because remember, they depend exponentially on this integer parameter r. But the match between the value and the upper bound is fairly good. In fact, we had to compute almost all the signs here, digits, to get to pinpoint the difference between the actual value and the upper bound. There is some gap to the lower bound. All right, then, strongly regular graphs. We have more examples, but for this talk, I just chose one from each series. So let us take an SRG given by points on a quadratic. So these are the parameters taken from the tables of SRGs from Andries Brouwer's online tables and his recent book. There is a standard way of making a spherical code out of an SRG by projecting a standard basis on the eigenspace of the adjacency matrix of the graph. And for instance, projecting on the space of this dimension, we obtain a spherical code with the sum of distances of this form. And if we compute the upper bound, then the order matches. The constant for the upper bound is 828. And what we subtract here is slightly more, 884. So this is below the upper bound, but fairly close to it. This is probably a good place to say that we didn't find any new minimizers. Why new? Well, because there are the known minimizers. They are the universally optimal codes of Kohn-Kumar. They all minimize the sum of distances. It doesn't mean that there couldn't be further minimizers that are not universally optimal, but we don't have such examples. It would be nice, but well, we couldn't find them. Let's say spherical embeddings of binary codes. We took this remarkable construction binary code by Sidelnikov from 1971. This is again an infinite sequence of binary codes with length of this form and that cardinality. And the weight distribution, they are codes that have two non-trivial weights. W1, W2, that many vectors of W1, that many of W2. Put them on the sphere, compute the sum of distances so that this CR tilde is the spherical embedding of this binary code. So here is the asymptotic formula. And indeed, I needed to compute many terms because the first three coincide with the upper bound. It is only the third where we have a little, the fourth where we have a little discrepancy. So these codes are very, very close to the upper bound, even though they don't quite match it in the asymptotics. And here is the lower bound. So this is n to the 7/4, and here we have 5/4. Again, we compute a few numerical examples. Well, for small dimension and cardinality, everything coincides, the lower bound, the upper bound, and the value. Not exactly, no, but fairly closely. And then the values follow closely the upper bound. Of course, we looked at the familiar, the usual suspects, the Quadratic codes themselves, dual BCH codes, constructed a few other examples, compared them with the bounds. So perhaps it is a good moment to say why the classic setting is indeed richer than our setting, even though I had been curious for a while. Why do people consider fixed dimension and growing cardinality and not growing dimension? Well, because in growing dimension, the main term of the asymptotics is understood, and it is only the lower terms that we can play with. Now with these LP bounds, of course, we would like a general expression for the asymptotic bounds, but they are difficult or possibly even beyond reach. For instance, the Levenstein type bounds, we cannot compute them for arbitrary parameters. And so conceivably, these bounds will also not be computable. And well, that's where we stand with this problem for the sum of distances. This pretty much ends my talk. Thanks for your attention.
Thanks, Sasha. There were some loud claps in the room here, and everyone can find the reaction button at the bottom of the screen, and then we can clap more silently. And we'll open the floor to questions, please.